Welcome to my on-demand presentation on predicting pMDI formulation thermophysical properties using activity coefficient models. I am Dr. Joseph Camm of Canterbury Christ Church University. My co-author is Hendrik Versteeg of Loughborough University. The outline of my talk: the need for new pMDI propellants and the opportunities for new pMDI products. How we can use predictive engineering to aid the development of these new products. Why we need to understand thermophysical properties of pMDI formulations. I'll introduce a thermodynamic framework for predicting these properties that will be of great use in predictive engineering simulations. And I'll introduce the UNIFAC model. We have some results for HFA 134A ethanol mixtures to showcase the technique capability, and I will conclude with the outlook for our future work to provide predictive capability for formulation properties and for pMDI aerosol behavior and complementary experimental techniques. High global warming potential propellants such as HFA 134A and 227EA are to be phased out due to the Kigali Amendment to the Montreal Protocol. Global production will be greatly reduced, so alternatives will be necessary. A promising alternative is HFA 152A, difluoroethane. Products will need to be reformulated and devices may need to be reoptimized. However, there may also be opportunities to improve formulation device performance. Here we see typical product development strategy for new formulations. Multiple iterations of trial formulations and performance measurements in the form of, for example, aerodynamic particle size distribution, APSD, are performed, the process often being based on experience. However, there are multiple multi-scale physical processes occurring during the dose preparation, atomization, and spray in a metered dose inhaler, as we know. With the capability to accurately predict formulation thermophysical properties, as discussed in this talk, comes the potential to use predictive engineering simulation to reduce the number of development iterations and gain and capture insight into the physical phenomena, ultimately governing APSD and other performance metrics. So which properties do we need to know? The key thermophysical properties are listed here. Importantly, these are also crucial input parameters to any model of the aerosol formation process. Formulations containing ethanol require further attention due to mutual propulsion of the hydroxyl fluorocarbon functional groups in the liquid phase. We have identified initially the saturated vapor pressure, SVP, liquid viscosity, and surface tension as key controlling parameters for atomization and spray processes in pMDIs. Each of these are affected by the non-ideal thermodynamics of the ethanol and HFA mixture. Here are some schematics for models that can and have been used to predict spray and atomization of the kind found in a pMDI, and also of the kind needed to provide predictive simulation capacity. To describe and predict physical properties, it is proposed to use a thermodynamic framework based around activity coefficient models. Activity coefficient models represent the molecular interactions between liquid phase constituents, knowledge of which is key to understanding the bulk physical properties we want for our new formulations. There has been great success using activity coefficient models, such as UNIFAC, in the automotive and process industries, but within pharmaceutical, they have been confined to solubility predictions typically. The method is well suited to describing complex liquid phase constituents and the impact that these have on mixture properties. We have previously used both UNIFAC and UNIQUAC models to predict SVP, saturated vapor pressure, viscosity, and surface tension of both HFA 134A and HFA 227EA with ethanol. In this brief presentation, I will present some results for HFA 134A with ethanol at room temperature. UNIFAC uses tabulated interaction parameter data for pairs of functional groups, e.g. the hydroxyl and fluorocarbon groups interacting in the bottom left-hand corner of the slide. To our knowledge, this data is not publicly available for all types of fluorocarbon functional groups relevant to HFA propellants. Therefore, we have generated new interaction parameters using published measurement data for SVP, viscosity, and surface tension to complete the work presented here. The models used for surface tension and viscosity are described here. As discussed before, since the physical properties are influenced by intermolecular forces, they can also be described using the activity coefficient models. The viscosity predictions use the GC Unimod model described on the slide, which blends the UNIFAC activity coefficient prediction with an empirical viscosity parameter based on functional group content devised by the authors Chow et al. The surface tension uses the surface activity coefficient model shown on the right-hand side of the slide, which uses the UNIFAC activity coefficient predictions directly. For HFA 134A ethanol mixtures, we have simultaneously fitted data from the UNIFAC and GC Unimod models to the saturated vapor pressure, viscosity, and surface tension data for experiments conducted at 20 degrees Celsius. This used a nonlinear least squares algorithm in MATLAB with equal weighting for each data point. Here are the results from the fitting for each property. The UNIFAC model is able to represent the composition dependence of the physical properties, including the strong departure from Raoult's law for the vapor pressure. The RMS deviation and maximum deviation are given underneath the plot for each property. Experimental data sources used for the fittings are shown at the bottom of the slide. I'd like now to discuss the outlook for our future work in this area. We would like to continue to fit data to available experimental data for formulation thermophysical properties to compare and improve property prediction with experimental data and other methods. This will, of course, include looking at a range of temperatures and other propellants and more complex mixtures. We'd like to determine the best model for different applications and for different formulations. A future project would be to combine this thermodynamic modeling framework with a targeted set of experimental data gathering to create a genuinely predictive model for HFA 152A ethanol mixtures plus other relevant components. This would aim to construct a high-precision property database plus a consistent thermodynamic framework to describe those property measurements within and outside of the range of the gathered high-precision measurements. One promising set of techniques is the laser light scattering techniques. These can be used to gather thermophysical property data for metered dose inhaler formulations. Demonstrated here on this slide is the surface light scattering technique for simultaneous, non-invasive, high-precision measurements of surface tension and viscosity. A rig for making formulation measurements of this type using this technique has recently been constructed at Loughborough University. Many thanks for your interest in our work, and comments and questions are always welcome, and here are our contact details.